Dear students, today we are going to discuss about UV visible spectroscopy of aromatic compounds. Consider the case of ethene molecule. It consists of two carbon atoms and it is sp2 hybridized carbon atom, and it has two unhybridized p orbital overlap together to form pi bonds, that is two atomic orbitals combine together to form two molecular orbitals. Due to the presence of pi electron, it have pi to pi star transitions. That is, the two pi electrons filled in bonding molecular orbitals. We know that ethene molecule has two pi molecular orbitals. One is bonding molecular orbital and another one is anti-bonding molecular orbitals. And the two pi electrons filled in bonding molecular orbitals which have lower energy than anti-bonding molecular orbital. Then due to this presence of pi electron, it goes pi to pi star transition when energy of certain wavelength absorbed. We know that the energy difference between bonding molecular orbital and anti-bonding molecular orbital, that is HOMO and LUMO, that can be designated as delta E, which corresponds to a certain value of wavelength. That is, we know that E is equal to Hc by lambda. An ethene molecule absorbs in the wavelength of approximately 171 nanometer. And this energy is sufficient to excite an electron from HOMO to LUMO. And that is the basics of UV visible spectroscopy, or it is called electronic spectroscopy. So, UV visible spectroscopy or electronic spectroscopy involves the study of electronic transitions from lower to higher quantized energy levels induced in a molecular species by absorption of energy in the ultraviolet and visible regions. Consider another molecule, buta-13-diene. It has four unhybridized p orbital, that is four atomic orbital combines together to form four pi molecular orbital. And this is the energy diagram. And here the four pi electrons are filled in the two bonding molecular orbitals. These two orbitals are bonding molecular orbitals and these two molecular orbitals are anti-bonding molecular orbitals. And this is our HOMO, that is highest occupied molecular orbital, and this is our LUMO, that is lowest unoccupied molecular orbital. Here the energy difference between HOMO and LUMO, that is delta E, is smaller than our previous molecule, that is our ethene. We know that energy and wavelength are inversely proportional. That is, as energy decreases, wavelength increases, which means this molecule, that is our 1,3-butadiene, absorbs in a higher wavelength region than our ethene molecule, and it is approximately 217 nanometer. That is, as conjugation increases, the energy required for an electronic transition from the HOMO to the LUMO decreases. That is, delta E will be small as conjugation increases, and consequently the absorption shifts to longer wavelength. That is our bathochromic shift. Then consider the case of hexa 135 triene. It consists of 6 2p orbitals unhybridized. That is, 6 atomic orbitals combined together to form 6 pi molecular orbitals, in which 3 are bonding molecular orbitals and 3 are anti-bonding molecular orbitals, and 6 pi electrons filled in the 3 bonding molecular orbitals, and this is our highest occupied molecular orbital, and this is our lowest unoccupied molecular orbital. Here the energy difference between HOMO and LUMO is smaller than previous molecule, that is our buta-13-diene, which means wavelength will be more higher than the buta-13-diene. That is, hexa 135 triene absorbs in the region of approximately 255 nanometer. That is, as conjugation increases, it undergoes bathochromic shift. Or according to molecular orbital theory, we can say that conjugation moves HOMO and the LUMO closer to each other. That is, conjugation increases the energy of HOMO and decreases the energy of LUMO. This is the schematic representation of UV spectrum of buta-13-diene. Here, lambda maximum is observed at 217 nanometer. Next, we have to compare the UV visible spectra of acetone and methyl vinyl ketone. An aldehyde or a ketone has both pi electrons and non-bonding electrons or lone pair of electrons present in oxygen. Therefore, aldehydes and ketones show N to pi star transitions and pi to pi star transitions. So, acetone in hexane is a solvent which shows characteristic N to pi star absorption at lambda maximum at 279 nanometer, and pi to pi star transition has lambda maximum at 187 nanometer. Pi to pi star transition is not commonly observed in the 200 to 800 nanometer region of spectrum. So, acetone shows a characteristic N to pi star peak at 279 nanometer in hexane. Now consider the case of methyl vinyl ketone. It has two characteristic transition. One is pi to pi star transition and another one is N to pi star transition due to the presence of non-bonding electrons. Both the lambda max values of methyl vinyl ketone are seen to be at longer wavelength than the corresponding lambda maximum values of acetone, because methyl vinyl ketone has two conjugated double bonds. We know that conjugation raises the energy of the HOMO and lowers the energy of the LUMO. Consequently, a lower amount of energy is required for the pi to pi star transition for a conjugated system than for a non-conjugated system. So, for methyl vinyl ketone, the pi to pi star transition has a lambda maximum at 219 nanometer, and the N to pi star transition has a lambda maximum at 324 nanometer in normal hexane solution. Next is an aromatic compound, benzene. It is the simplest aromatic compound with a delocalization of pi electron system. Due to the presence of pi electron, it has pi to pi star transition. It shows two primary bands with lambda maximum at 184 nanometer and 200 nanometer, and a secondary fine structure with lambda maximum equal to 255 nanometer in cyclohexane as solvent. Here the first band is due to an allowed pi to pi star transition, and this is the intense band, whereas other two bands are due to forbidden transitions. And the only absorptions with fine structure is seen in the 200 to 800 nanometer region of the spectrum of benzene. The fine structure arises due to the vibrational effects on the pi to pi star transition. This is the UV visible spectrum of benzene showing vibrational fine structure. That's about UV visible spectroscopy of organic compounds. Hope it is clear. Thank you.